All right, folks, it's Fast Action, Back in Action. In this video, we are going to look at the area of a circle. We're going to develop that formula for the area of a circle. And then we're also going to look at how to find the area of some specific shaded regions that will, of course, translate into slightly different shapes in our lesson and examples in class. All right, so up here at the top, we're going to look at the area of a circle, and you may already know the formula for the area of the circle to be pi r squared. Now, what I told you in class is that I was going to take every shape that we're going to do and we're going to turn it into a rectangle or a parallelogram that of course could be turned into a rectangle to help us understand how that's going to happen. And we're going to do that with the circle as well, but it does require a little stretch of your willing suspension of disbelief. So we have to kind of stretch a little bit here. What I want you to notice is I have my circle here, and then over here I've drawn a parallelogram broken down into some triangles. Now, what we're going to imagine is happening here is we are going to take 4 of these triangles, these pieces of our circle, and we're going to imagine that those 4 pieces have been taken apart and they're going to become these 4 triangles right here. Now, where this requires us to kind of stretch our mind, though, is that what we know is that this outside of the circle is curved, but when I've drawn my parallelogram here, I made these sides straight. Now, I only divided it into 8 pieces, but what we can understand is that if I did, in fact, divide this into smaller and smaller and smaller and smaller and smaller little slices, it would eventually have the appearance of being straight. And that's what we're kind of imagining in our mind. So I've taken 4 of them and I put them face up, which means these other 4 are these 4, okay? Now, if I was looking at this parallelogram and I wanted to calculate the area of this parallelogram, I would first say, okay, how long is this side of the parallelogram, this base? And when I come back over here to my circle, I can see that, oh, that side of the parallelogram is 1/2 the perimeter of the circle, okay? And then the height of each of these triangles, and again, this is where it requires a little bit of our stretch of imagination. The height of our triangle is going from the tip of the triangle to the edge of the triangle. And what we can see over on the actual circle is any segment that goes from the center or the tip of a triangle to the edge is actually going to be a radius. So in our picture, because these aren't drawn really small, it feels like this is actually different than this. But in reality, when we look at the actual circle, they would be the same. Okay, so that distance is going to actually be the radius of the circle, which means the area of this parallelogram is the radius of the circle times 1/2 the perimeter of the circle. Now, if we continue expanding this formula, we have our radius and then we have 1/2. And of course, the perimeter of the circle can be expressed as 2 pi r. And then if I clean that up a little bit more, of course, the 1/2 and the 2 will cancel. So we will actually get that the area of the circle is pi r squared, which was exactly what we wanted to get, okay? So just wanted you to have some comfort with that and kind of see where that comes from. Now we're going to do a quick review of arc length. And what we learned in the previous semester is that arc length is a portion of the circumference. And what I've done here is I've written our formula both ways, the way we worked on it in class. So the portion piece is going to be this arc measure over 360. That tells us what portion we want. And then, of course, the circumference of our circle would go right here. And then, of course, of is what translates to our multiplication. So our portion of means we're going to multiply the portion times the circumference. Many of you also did arc length working with the proportion, which means we just took this formula and rearranged it so it looks like a proportion. Remember, I don't really care which one you use. I just need you to be comfortable with one or the other. Okay, so now what we're going to do is our quick review is we're going to find the length of our arc ZAP. So of course, arc ZAP needs to be this arc the long way around. That's how we know. Which means when we go to do the arc length, we're going to need the number of degrees that goes with arc ZAP. So when we look at our picture, I gave you the arc measure or the angle measure for the small angle, so we are going to need to flip that to find the one that we actually want to use. So we're going to use our 320 degrees. Okay, so what I want you to do is I want you to just pause the video and then practice, and you choose whichever method you want to do to find the arc length. Remember, we are not converting anything to mixed numbers. We are not converting anything to decimals. All things need to be left as simplified fractions. Okay, take a quick look. Make sure that you got the right answer. Notice that no matter which technique we use, we do get the same answer either way, so it makes no difference. Remember, we are leaving things as our simplified fractions. So notice on the proportion method, when I got to here and I cross multiplied, I initially left this separated just to help me be able to simplify a little bit easier and reduce so that I wasn't as reliant on my calculator. All right, so this is our review of arc length. Now, the first special shaded region that we're going to look at down here is going to be called a sector. Now, a sector of a circle, you can see, is this shaded region here, and it looks like the whole piece of pizza, so to speak, versus the arc length was really just, we could think of it as the crust of the pizza. Now we want this whole piece of the pizza. Well, the difference between the area of a sector and arc length is very, very little. That difference is very little. The arc length was a portion of the circumference, and the sector is going to be a portion of the area. So all we're going to do in these two formulas is we're going to swap out circumference in these two formulas for area. Okay? That's the only thing that's going to change in the formula. The technique is going to stay exactly the same. So if I'm going to slide this up, and we're going to go ahead and set these up, and then I'm going to let you pause it and do the math. So if you were using our proportion technique, you would set your problem up as a 120, because that's the number of degrees that goes with our shaded region, over your 360. And you don't know the area, so you're going to put the variable in there. And the area of our circle, using our formula from the top of the video, is 36 pi. Or if you were using the definition technique, you would say that yours is going to be the area of the sector, your portion, that's 120 out of 360 is your portion, of means multiplication, the area of the circle. Okay, so again, pause the video and make sure that you can simplify and reduce that and get to the final answer. Okay, did you get 12 pi inches squared? Make sure you're labeling your answer. I didn't do all my reducing, but I would have the 3 would go into the 36 12 times, and then I could multiply my fraction straight across. Okay, now sectors of a triangle, or a segment of a triangle, is going to be a sector minus the triangle. So when you hear this vocabulary word segment of a circle, it's talking about this little shaded region. So what we could imagine is that we had this whole piece of pizza, and we didn't want to eat the crust, so we just chopped off the crust. Instead of making a nice curved line, we just chopped it off, and this is that piece of the crust that we just chopped off. Okay, so what it's going to be is a sector, and then we're going to have a chord, and so it will be the area of the sector, the whole big sector. So we'll have this whole big sector, and we're going to subtract from that the area of the triangle. Now remember, whatever triangle you have there is going to be an isosceles triangle, okay? No matter, because all the radii in the circle are the same. So this triangle is always going to be isosceles. Now in this particular example that I'm working with here, this triangle is in fact a right triangle, which makes this one even easier for us. So we can fill that in. So this is going to give us a chance to practice the sector and practice the triangle again. This time, our sector is going to be really easy because our portion is 1/4 of the area of the circle. So again, I want you to pause the video and I want you to practice finding the area of the blue sector and the area of this nice small red right triangle, and make sure that you can get those correct. Okay, the area of our sector ended up being 64 pi. I wrote out the initial step, the 90 over 360, but if you had already seen, as I discussed, that this was going to be 1/4, you could have just automatically reduced your portion to 1/4. And then over here, I did my 1/2, my 8 times my 8. Now, when we get to class, we're going to look at what happens and we're going to practice with triangles that are not right triangles. Remember also on the area of your sector, if you didn't set it up this way, you were certainly welcome to use the proportion technique, but either way, you should have gotten 64 pi for the area of the sector, 32 for the area of the triangle. We leave it in this exact form unless we're asked otherwise. And remember, the order of the subtraction does matter. Our last one is going to be called an annulus of the circle. So an annulus is formally a big circle minus a little circle. So it's the shaded region in between the two. We are also going to look at problems where the annulus isn't a circle in a circle. Maybe it's going to be a square in a circle, or maybe a hexagon in a circle, or flip-flopped. We're going to look at a lot of different kinds, but they all come down to this idea of the big shape minus the little shape. So this one's going to go really, really fast, and we're almost done here. The area of the big circle, they gave us that radius, and they said the radius of the big circle was 20. So we would have a 20 squared pi, and then we would have the radius of the small circle is 17. And then, of course, we would clean that up, and we'd say, oh, that's 400 pi. And we'd say minus our 289 pi, and we would subtract that, and we would get our final answer of 111 pi, and we'd say, this time we don't know the units, and we'd say units squared. And that's all we've got. When you get to class, we're going to do a whole bunch more. If you flip the page in your notes, you'll even see that we've got a whole bunch of very, very different looking shapes that we're going to work with.